So let's discuss the concept of multi-carrier communication, and we will also look at what is the advantage of multi-carrier communication and what are the implementation issues associated with multi-carrier communication, which is later solved by the concept of OFDM. So let's first discuss what is the concept of multi-carrier communication. In multi-carrier communication, we transmit various constellations or the same constellation over various frequencies simultaneously. So let's understand it through this figure. So this is the frequency centered around, or this is the cosine of sine, and this is the cosine, this is the sine of frequency f1. This is I and Q channel corresponding to frequency f2. This is I and Q channel corresponding to f2. This and this is I and Q channel corresponding to some frequency fn. So in single carrier modulation we use both I and Q channel for corresponding to only single frequency, which we denoted by fc till now. But now we will transmit all the will transmit the symbols. So if we are using here some QAM constellation or QPSK constellation or ASK constellation, we will transmit each of this point through this IQ carrier constellation, this through this IQ carrier, and similarly this modulation, these symbols to this IQ carrier. So just denote this by, since we have taken the magnitude as A1, just denote it by some point as P and Q, or capital, not Q, because we have used some U and V maybe. So each of this constellation point has some in phase value and quadrature phase value. So U is the in phase value, V is the quadrature phase value, right? Or you can also write it like this. Okay, let us take it as U comma V for time being. Since it is corresponding to frequency f1, take it as U1 V1. This is U2 V2. This is U3 V3. So U1 V1 can take any value of this constellation, can take any value from the constellation C1. It can be either QAM or QPSK. Similarly, UN and VN can take value from the nth constellation, and this frequency which will be sent through the frequency f1 or IQ channel corresponding to frequency fn. So if you draw its transmitter would look like this. Decays are the input bit sequence 0 1 0s 1s, and just assume that each of this constellation is same and it is a M-array constellation. It means there are M number of constellation point at each of the constellation. So what would you do? We will first take log 2m multiplied with n, where n is number of subcarriers. These all frequencies are denoted as subcarriers or carriers you can call, or just for time being let's call it carrier. N is the total number of carriers and m is the constellation size of each constellation. So for time being, we are assuming that all of these frequencies are using same constellation, same M array constellation. So therefore, we will first take log 2m multiplied by n number of bits, and then for the first constellation, for the first carrier, for the second carrier, and for the nth carrier, we will map it to one of the constellation point. So it is a bit to symbol mapping. For example, we want to transmit 0 0, we can map it through this point, which will have some I value and some I value and some Q value, and then you will multiply the ith part by this and qth part by this. So this is what we do. So multi-carrier communication is many parallels single line communication, right? Single carrier communication. So in phase of this will be multiplied with cos 2 pi f1t, and q phase will be multiplied with sine, and then we will send it, right? Similarly, how many bits will go here? Log 2m number of bits. Here also, because you are using m point constellation, so log 2m number of bits will be required. Log 2m. So therefore, total of n into log 2m number of bits will be required. Similarly, this will be m point constellation, and we will multiply the in phase part by I carrier and q phase part by q, and then we'll sum and sum. And further we will sum all of these carrier. Therefore it is called multi-carrier, because you are simultaneously transmitting your information over multiple carriers. This is carrier corresponding to multi-carrier communication. So this is the concept of multi-carrier communication. So what would be the time duration of the output? If this is the signal of this multi-carrier signal, what would be the output duration? Since each of this, since you are taking how many bits at a time? Log 2m into n. So the duration of each will be log 2m multiplied by n into t. So let's further understand it through an example. If m is equal to 4, we are taking 4-point constellation, and n is equal to, or just take m as 8. So you are taking 8 PSK, for example, for the modulation, and there are 4 different carriers which you are using. So as soon as, so this n will be 3, or n is equal to log 2m, not n, sorry, small n is log 8, which is equal to 3. So as soon as 12 bits arrives from the source, it may be any combination. So as soon as 12 bits arrives, what you will do? You will send these 3 bits to these, because you are using 8-point constellation, and assume that you are using 8 PSK. So you will map it to this constellation point, and then you will multiply it with the in phase and quadrature phase carriers, and you will sum it and send. This will be sent to the other 8-point constellation. This will be sent to this will be sent to this. So first we will wait for how many bits? 12 TB, and then we will distribute it to 3, 3, 3, 3, 4. So total time which we have for the transmission is 12 TB, which is equal to log 2m into n TB. So the duration of the carrier or the multi-carrier signal is log 12 TB. So next point is, what is the advantage of using this multi-carrier scheme? So if you remember, here we have said that we will transmit. So each of this I and Q, so each of this will have 12 TB of duration, right? And summation of all will also have 12 TB of duration, right? So what is going on here? If it was a single carrier system, what would you do? You will take 3 bit at a time. Only one carrier is there. Only, for example, you are using this carrier. So every time you send 3 bits, 3 bits, 3 bits, 3 bits, and for 3 bits, one of the point will be selected and one signal will go out, right? So if we, for the same example, had we used single carrier scheme, what will we do? We will first send 3 bits, then we will again send 3 bits. So 3 TB, 3 TB, and so on. Here what we are doing, in carrier 1 we are sending 3 bits, in carrier 2 we are sending 3 bits for how many duration? 12 TB of duration. So if you draw power spectral density of single carrier scheme, the bandwidth occupied will be directly proportional to 1 upon the length of each transmitted signal, which is 3 TB in this case. So it will be log 2m TB. Let's donate log 2m TB by TS. So bandwidth with it single carrier will be 1 upon TS. But in this case, since power spectral density for each carrier will have bandwidth directly proportional to 1 upon 12 TB, which is log 2m multiplied by TB. Since log 2m TB we have taken as TS, it will be equal to 1 over NTS. So bandwidth occupied by each of the subcarriers reduces by the factor of capital N, which is number of carriers. So number of carriers which we are utilizing, why we can reduce the power bandwidth of the signal by the 1 by n. So what is the advantage of doing so? So advantage of doing this will be, and just one more point, that this bandwidth will be centered around frequency f1, this bandwidth will be centered around f2, and this bandwidth will be centered around fn, right? So total bandwidth occupied by all this signal will be same, but each of the carrier will occupy the smaller bandwidth. Let's understand it further with the diagram. So if this is the total bandwidth, this is first null of the power spectral density curve. You can, if this is center frequency, fs plus b by 2 and fc minus b by 2. So in single carrier, what will you do? We will send through fc and the total occupied bandwidth will be this much. But here you are using multiple frequencies in such a way that each of the frequency, so this is a carrier f1, so you can assume this is f1, this is f2, this is F3. So total bandwidth occupied by F1, F2, F3 centered around F1 will be B by N, because if you say 1 by Ts is B is 1 over Ts, so the bandwidth occupied will be equal to B by N by each of the subcarrier. So this is the advantage. So total bandwidth you are utilizing. So this is the bandwidth available from the channel. In single carrier case, we try to use whole bandwidth, and therefore this type of symbol duration we choose. But in multi-carrier scheme, we choose many frequencies such that we utilize the complete spectrum. However, each of the subcarrier will have bandwidth of B by N. So what happens when each of the subcarrier is having bandwidth of N? If you just observe the response, this is the response of the channel, see, this is you can assume that this is a response of the channel, and we try to put your power spectral density or your signal inside this bandwidth only, inside this band only, right? So what would happen if you see that this part, for this duration of bandwidth or frequencies, for this range of frequencies rather, our channel is almost flat, and therefore what would happen, for each subcarrier the channel will act as a constant response channel, constant impulse response, or constant frequency response channel. So the frequency response or the amplitude of the frequency response of the channel is almost constant, and therefore the distortion will be less for each subcarrier. So in effect, had you used a single carrier setup, and this was the the frequency response of the channel or magnitude of the frequency response of the channel, what would you do? You will try to put your signal inside that, and if you remember, the bandwidth occupied by the signal is 1 over Ts, so we will try that B is equal to if this is B by 2, then bandwidth is directly proportional to the symbol duration. So symbol duration will be Ts for single carrier scheme, but for multi-carrier scheme, if you see, the bandwidth you utilize is the bandwidth occupied by each subcarrier is B by N, and here the whole frequency will be, whole bandwidth will be occupied by only single carrier. So the signal corresponding to single carrier will go through the distortion, because the response of the channel is not constant over all the frequencies, but here the response of the frequency is, the channel is almost constant over all the frequency range over each subcarrier. Therefore each subcarrier will go through less distortion. So this is the importance of using multi-carrier. So let's take a practical example. So if we transmit a multi-carrier signal through wireless channel, if we transmit our multi-carrier signal through wireless channel, and wireless channel, the duration or the range over which frequency range, if we just draw the frequency response of the wireless channel, the frequency range over which the response is almost constant is known as coherence bandwidth. Known as coherence bandwidth. And therefore, when your signal or the what is the if bandwidth occupied by signal is less than coherence bandwidth, then there will be less distortion, and this distortion is named as inter-symbol interference due to multipath. So what we are discussing here, that this concept was in general, that you have any frequency response of a channel, and if you can make sure that your signal lies inside the flat portion of the frequency range, the distortion will be less. But now we are discussing a particular example when we are taking a wireless channel, and the frequency response of a wireless channel and the range over which the frequency is almost constant is known as coherence bandwidth. So if we put the bandwidth occupied by signal less than the coherence bandwidth, the distortion will be less, but this distortion occurs in wireless channel due to ISI due to multipath. What is ISI? ISI is inter-symbol interference. So let's try to understand the interference, because wireless channel is a multipath channel. So in wireless channel, how we evaluate the coherence bandwidth, let's discuss it. Wireless channel is a multipath channel. What is a multipath channel? Multipath channel is when we transmit a signal. This is your base station, this is our receiver. So if we transmit a signal, the signal comes to the receiver through multipath, through various paths. So if this is the signal which you transmit, this is the line of sight. So the signal will come with some delay, and another path which is another delay, and the longer path, so another delay. So you will see the same signal is received by the receiver through multipath, and the overall signal will be summation of this. So what would happen if the delay, so what is delay? So this is the starting point of the first, so this is the delay. So if the delay of the signal is more than the symbol duration, of course, so this signal will interfere the next or the next symbol. So this will create inter-symbol interference, that the previous symbol is interfering with the next symbol if your delay is more than TS. Delay, TD is also known as delay spread. So if delay spread is more than the symbol duration, so this TS is not, so don't confuse, just write symbol duration. Symbol duration. So what is the so if your delay spread is greater than the symbol duration, what is the symbol duration in case of single carrier, and what is so yeah, so what is the relation between coherence bandwidth and delay spread? BC is equal to, almost equal to 1 upon delay spread. So more the delay spread of a wireless channel, lesser is the coherence bandwidth. So for example, if your delay spread of a channel, your wireless channel is 1 millisecond, so what should be your symbol duration? In single carrier scheme, if you remember, 1 upon TS, TS is log 2m TB. In multi-carrier scheme, it is 1 upon, sorry, is TS, not 1 upon, it's TS. And for the multi-carrier scheme, it was equal to NTS, because each of the subcarrier, so each subcarrier has a symbol duration of NTS. So for 0 ISI due to multipath, your TS should be greater than, or the symbol duration should be greater than TD. This is the condition for ISI, and this is condition for no ISI. So if no ISI due to multipath, always remember that this is the ISI due to multipath. So as you can see in multi-carrier scheme, symbol duration in multi-carrier scheme is greater than the symbol duration in single carrier scheme, which is of course n times the single carrier scheme. Therefore, there is a high probability that this will be greater than TD rather than this, and therefore each of the subcarrier will be free from ISI due to multi-path. We will further discuss this in the later class.